Hello, Professor Hicks and all students in System and Software Security class. I am Antarip Sahu, graduate student in the Computer Engineering program. I will be presenting the paper on model-based steganography. Model-based steganography is a paper published by Phil Sallee when he was a PhD student at University of California, Davis. I will refer to him as Dr. Phil Sallee or Dr. Sallee or the author throughout this presentation. Briefly, I will discuss the abstract of the paper. The author uses a statistical model of the cover medium to perform steganography and steganalysis. Further, the author discusses how the previous steganographic methods were prone to simple statistical attacks. The author shows through proof of concept how model-based steganography achieves higher efficiency and message capacity, remaining secure against first-order statistical attacks. An introduction to steganography. Steganography comes from the Greek word steganographia, where steganos means covered or concealed and graphia means writing. Steganography is a technique to hide a message within another message or a physical object. Steganography conceals not only the message but also the existence of the message. For example, in olden days, when someone had to share a secret with someone else, what he could do is he would write a normal letter but write the secret message with invisible ink. The receiver would just have to heat the paper or put some chemical on the paper to decipher the secret message. There were many other ways in which people would use steganography in the past, but for our discussion, we'll go ahead with an example of digital steganography. I would also like to discuss about cryptography. Cryptography involves mathematical operations to manipulate data to an unrecognizable form. The unrecognizable form, known as the ciphertext, can then be transmitted to the intended receiver. However, attackers can intercept the ciphertext that is being transmitted and try to crack it. Therefore, in case of steganography, it is not known whether even such a transfer of information is even happening or not, but it is known in cryptography. So, steganography is not the same as cryptography. Recently, digital steganography has had a lot of developments, and it can be broadly classified based on the cover medium, which could be text, image, audio, or video. Steganography is useful because it is very time consuming to find out the hidden message and can also get very resource intensive to crack. Now imagine if steganography is used as a threat. Is it practical to decode the message or destroy the medium? I would like to briefly discuss about JPEG images. JPEG or JPEG stands for Joint Photographic Experts Group. JPEG is a compression standard where we compress digital images to save storage space. The file format is known as JPEG or JPEG file interchange format. We will continue to use the term JPEG image in this presentation. I will discuss how JPEG compression takes place. The image in the RGB color space is transformed to the YCBCR color space, and in the YCBCR color space, the image is broken down to the luminosity and the chrominance layers. Then we take 8 pixel by 8 pixel blocks and we perform direct cosine transform 2 to generate 64 cosine functions, and we update the blocks with the values of the coefficients of these functions. Now we have high frequency and low frequency functions. What we will do in the next step, which is quantization, we will try to remove the high frequency data, and after that we will be doing Huffman encoding to reduce the data size. Then we have our image with JPEG compression. I would like to mention here that quantization and encoding are two very important steps with regards to steganography, because over here we determine the coefficients where we could actually encode our secret message. In order to get the image back, we just reverse the steps that I have mentioned. I would like to mention that in the reverse order we use inverse direct cosine transform or DCT3, and we will notice that because of the quantization and encoding steps, some of the high frequency information will be lost, and that's why we have JPEG as a lossy compression. I have an interesting question here. Can we use lossless format like bitmap or PNG for steganography? The author discusses about two previous steganographic methods. First, F5. In case of F5, instead of flipping the least significant bits to encode the image, F5 increments or decrements the coefficients to maintain histogram. However, the change is detectable by estimating the original image from a cropped and re-JPEG'd version of the image. Therefore, the differences between the steganogram's histogram and the estimated original's histogram becomes quite evident. F5 is hence prone to marginal statistical attacks. Outguess is the second steganographic method. Outguess preserves marginal statistics by correcting the global coefficients. Outguess reserves half of the coefficients for the purpose of correcting the statistical deviations caused by the changes in the least significant bits in the other half. However, because of this, capacity is reduced. Now we come to the most important question. Why is the author suggesting model-based steganography? There are two reasons: to avoid marginal statistical attacks and to achieve maximum capacity. Now I will describe the model. I will start with the encoding part of the model. We take cover media X and split it into X alpha and X beta. X alpha stays the same. X beta will be replaced by X prime beta, which will contain the encoded message. X alpha will be the most significant bits and coefficients not selected to encode the message. X beta will be the least significant bits which will carry the message. The model distribution p hat x will be estimated over at all possible values of random variable x beta over random variable x alpha. We select x prime beta to obey this conditional distribution. By carefully choosing the random variable x alpha and random variable x beta, changes to x beta will be difficult to detect by human perception. The lack of precision by humans is what least significant bit encoding method takes advantage of. The conditional probability distribution and the encrypted message is given to the entropy decoder to generate x prime beta, and combining x alpha and x prime beta, we get x prime, our steganogram. Now I will discuss the decoding part of the model. To recover the message, the steganogram is divided into x alpha and x prime beta. X alpha is fed to the model p hat x, which is used to compute the conditional probability distribution of random variable x beta over random variable x alpha. The same model is given to the entropy decoder, which decodes the encrypted message. Here, I would like to mention that the message that was carried by the cover media could already be an encrypted message using either private key or public key encryption. The important point here is that the cover media is only carrying a message, irrespective of the method of encryption chosen for the message. Capacity is defined as the ratio between the size of the message and the size of the cover medium. We would want to find out how large a message can be hidden inside a cover message. If the random variable x beta is considered to be used as an information channel, from information theory we have the entropy of the conditional probability distribution given by this formula. We can measure capacity for given x alpha with this formula. The author also discusses how to perform steganalysis using the model discussed in this paper. If we have a target message and we suspect that it has a steganographic system encoded message, Using a weaker model than the one presented in this paper, we can find out using entropy the expected message length. We can use the steganographic decoding and measure the length of the resulting message. And we could compare both and find out if any steganographic encoding has been done in the target message or not. Now I will discuss how we apply the model to JPEG images. The model consists of parametric description of marginal DCT coefficient densities. We will ignore the DC components and the zero value coefficients. We will be using the AC components of the DCT coefficients and encode the message within them. What are DC coefficients? They represent mean luminance within the 8 by 8 block for JPEG compression. In the embedding algorithm, we compute low precision histograms of each type of AC coefficient. If the embedding step size is 2, there will be two possible offsets within non-zero bins. The bin indices which remain unchanged will comprise the X alpha, and the bin offsets will comprise X beta, where we would encode our message. The figure to the right shows the DCT basis functions and also shows the DC coefficient and the AC coefficients. The figure to the left shows the histogram of DCT coefficients for a sample image measured in log probability and the model density after being fit to the histogram using maximum likelihood. A pseudo-random permutation is used to determine the ordering of coefficients. The message and symbol probabilities are passed to a non-adaptive arithmetic decoder in order to obtain symbols specifying the new bin offsets for each coefficient. The resulting symbol comprise X prime beta. I would recommend the audience to go through the paper to observe how the model suggested in this paper is implemented on a JPEG image with intricate details. Now I will discuss the embedding efficiency of the model. What is embedding efficiency? It is the average number of message bits embedded per change to the coefficients. The more changes in coefficients, the easier it is to detect the steganography. Let K represent the probability of one of the two offset symbols for a given coefficient. We have a formula to calculate the expected embedding efficiency. We find that the expected embedding efficiency is never smaller than 2, as K is a probability value between 0 and 1. I will now discuss the maximum message capacity and the embedding efficiency of the previous to steganographic methods. F5 has maximum message capacity of 13% with embedding efficiency of about 1.5. Outguess has maximum message capacity of about 6.5% and embedding efficiency of close to 1. We find that the model suggested in this paper has an embedding efficiency of 2 or more, and I will discuss about the maximum message capacity in the next slide. Now I will discuss the results of model-based steganography. The author tested his model-based method on grayscale JPEG images of quality factor 80, and he also suggests that it could be applied to color images as well. Referring to the figure in the left, we find the coefficient histogram of DCT coefficients before and after the application of F5 and model-based steganographic methods. We find that model-based method generates a histogram which is very similar to the original message. You could notice that the histogram by F5 method has stark differences when compared to the original message. A quick look at the table to the right shows the maximum capacity and the embedding efficiency of various images where model-based steganography was applied. We find the maximum capacity is around 13% and the embedding efficiency is over 2. In summary, the author has successfully presented model-based steganographic methods and explained how it is effective for both steganography and steganalysis. He has given a statistical model and described the methodology to determine maximum message length. As a proof of concept, he has applied model-based steganography to JPEG images and has shown how it is effective against marginal statistical attacks that F5 steganographic method is prone to. He has also demonstrated that model-based steganography has higher maximum message capacity than outguess algorithm. He is promoting a promising outlook towards using advanced statistical models to design sophisticated steganographic algorithms as a future research area. The author has some suggestions for future work. He would like to extend this line of investigation to other carrier media, for example, MP3 audio files, video files, and other image file formats. He would also suggest further improvement in the statistical model. He would also like other researchers to explore the wavelet domain for embedding the message. There are a lot of new developments in the field of steganography, and the audience who are interested to know about the latest developments can refer to these 3 papers that I have listed here. These are the references that I have used to prepare this presentation. Here is a list of interesting online resources that I have referred to while preparing this presentation. You can address your questions, comments, and feedback to my email address. We have reached the end of the presentation. I would like to thank you very much for listening.